Hi, I'm Susie Rock from ADAS, and I'm just going to talk about some field experiments we've done as part of the INNO-VEG project. In ADAS, we've been running field experiments on a variety of crops since about 2015, and we now run about 200 experiments per year, mostly on arable crops, on wheat, barley, oilseed rape, which are assessed using yield mapping. But the lessons that we've learned and the approach we've developed for those crops also apply to vegetables. And all of these experiments are run in cooperation with farmers, where the farmers are applying treatments and harvesting the crop as usual. And we're testing treatments that are of interest to them. The innovation is that we're using crop reflectance data to assess the treatment effects on the crop, and using spatial statistics to analyse that data to get precise and robust results. The first lesson that we've learned from doing all these experiments is that the choice of field is really important to running a good trial. The more even the field, the more precise the results. We accept that every field has variation, and the difference between the highest and the lowest yielding parts of the field are going to be larger than any treatment effect that we're likely to see in our trials. And so we recommend always checking out a field and thinking about it before starting an experiment. For me, the first place I would go is always to Google Earth, where you can get historical images of historical field images showing where there used to be field splits, where fields have been joined together, because that difference in field history can affect yield for easily 20 years after the fields have been joined. We might also look at previous yield maps, because the variation tends to follow the same patterns from year to year. And satellite data is available on a wide range of farm management softwares and platforms. This image is from datafarming.com, an Australian website. It's a freely available image. And you can see that in this field, although there's quite big variation, it's going to be okay for a trial because it runs across the direction of travel, so that every treatment is going to experience the same variation. It's a fair experiment. And finally, we might get soil maps or nutrient maps to show the variation in a field. Having chosen a field, we then need to set out a good trial with respect to the underlying variation, and within that, we need to think about how many treatments and how to arrange them. Now, in a conventional plot experiment, you might test 10 or 20 treatments, and that's no problem. But in a large-scale field experiment, the ideal is just 2. The farm standard way of doing things compared with an innovation, a new test treatment, or at most 3 or 4 treatments. And by repeating these, we can get much more confidence in the results. If a field is just split in half, then those 2 halves will always yield a bit differently. And any difference, we can't really tell if it's the treatments or just the random variation, whereas repeating the treatments gives us confidence. So my first example was an onion trial from 2020, run on a commercial farm where they were keen to look at differences in nitrogen rate. You can see that the field that was chosen had significant variation at the north end, and so the trial was correctly placed at the south part of the field, and the treatments were repeated. 2 plots of the low nitrogen rate and 2 plots with standard rate. Because the treatments were applied with a spinning disc spreader using solid fertiliser products, we had to have two strips of each treatment, and the plot area was just the area between the tram lines, between the tracks, because the area between those two treatments has a mixed rate, there's an overlap. And we had quite a large difference in nitrogen rate, 130 kilos in the farm standard and 40 in the low rate. There were 2 drone flights using a multispectral camera that measured reflectance at 5 different wavelengths: red, green, blue, near infrared and red edge, which allows us to calculate a range of different vegetation indices, not just NDVI. But you can see from the NDVI image that already those 2 low nitrogen plots stand out in the field as being different. As well as the drone flights, we also had 12 yield validation plots where our technicians went out and hand harvested small plots, sorted the onions into marketable and unmarketable and weighed them so that we can look at the connection or the correlation between yield and vegetation index. And you can see that at both flights, but particularly at the second one, we had very good correlations. So these values are R-squared values, and they show the proportion of the variation in yield which can be explained by the variation in vegetation index. And so for NDVI at the second flight, 91% of the variation in yield is explained by NDVI, which is a really strong correlation. And to analyse data for the whole field, we first had to convert that high resolution image into data that we can statistically analyse, because our software is designed for yield maps, it's designed for point data. Because the onions are grown in beds, we didn't want to take data from the bare soil between them. And so using GIS software, QGIS, we created a grid of little squares, laid it over the onion beds, and within each square took the average value for the reflectance at each wavelength, and then calculated a vegetation index for each square. Because of the very high correlation between vegetation index and yield, we were able to convert that data into a map of predicted yield. So although we didn't measure yield for all of these big plots, we can predict it from the drone data and then run a statistical analysis to look at the treatment effect. We found at the standard rate we had an average yield of 71 tonnes per hectare, and that was nearly 13 tonnes per hectare higher than the low rate. And this value, 1.4, is the confidence interval, or the least significant difference. And because that is smaller than 12.9, we know that it's a highly significant difference due to the treatments. Our second trial was in vining peas, and that was run with a grower cooperative called HMC. They were interested in the impact of starter fertiliser on peas, but in setting up the trial before we got involved, they had 5 treatments, which is more than we would recommend, and those treatments were not replicated. But they were applied in nice, long, wide strips, taking in the whole field, and it was a well-chosen field with variation that was mostly across the treatments, although NDVI was always a little lower towards the west side. Pleasingly, the farm has chosen to repeat the trial in 2021, and they've improved the trial design. They've gone down to 3 treatments and increased to 2 replicates. And so we've had better and more precise results from the 2021 trial than we did from this 2020 trial. These are the drone images, 2 of which were done with a multispectral camera. And you can see the same patterns of variation that we saw in satellite images of the previous crop, but in addition, a lower NDVI strip at the left side, which coincides with treatments 1 and 2. Once again, we had validation plots, which were hand harvested and put through the viners so that we could correlate vegetation index with yield. In this case, the first flight on the 9th of June had the best correlations, and that fits with what we've seen in other vining pea experiments, which have shown that a drone flight at around flowering, about 2 weeks before harvest, gives the best indicator of yield. Uniquely, we also have an actual yield map for this trial, because HMCPs have fitted yield mapping technology to their fleet of viners. And so we can compare the predicted yield maps from vegetation indices with the real yield map. This is the results of analysing the real yield map. You can see an average yield of 9.76, and that the untreated control had significantly lower yield by 3 tonnes per hectare than that central treatment 3, and that was significant because the confidence interval is smaller. But the other 3 treatments, the differences weren't significant because the yield map was quite noisy. There's quite high errors on those results. But analysing the predicted yield maps gave us very similar results, similar average yield, similar treatment effects, but much greater precision because the data is less noisy. And that's why these confidence intervals are smaller, and most of the treatment differences are significant. These are the yield maps. You can see the real yield map looking a little bit gappy where it's been cleaned, and 2 maps of predicted yield. And none of them are perfect. Even a real yield map can over or underestimate yield depending how it's cleaned. But we think that this final yield map is actually the best indicator of yield. It's giving the same results, but cleaner data. And so, in conclusion, remote sensing data, crop reflectance data, can, for some crops, give a really good correlation with yield. And so it's an efficient and accurate way of assessing yield and assessing treatment effects in field scale experiments. But the precision of the results does depend on looking at underlying variation in the field, laying a trial out with replication and with reference to the field variation. And the INNO-VEG project is developing a framework to give guidance on how to do these kind of trials well in a whole range of crops. Thank you for your time, and I hope you enjoy the rest of your day.